just not something I particularly enjoy doing. So if it's a logic vulnerability, it's probably quite cool. And that's what kind of lends itself quite well to local privilege escalation, as you can find some quite interesting logic bugs in that. So what am I actually going to be talking about? Well, specifically, I'm going to be talking about Windows user mode sandboxes. So developing a technology to effectively mitigate remote code execution attacks. So for example, if you have a browser or a document reader and it's taking untrusted input from the outside, you want to actually, if someone can cause remote code execution in your application, you want to try and stop them from then taking that access and fully compromising your system. Now, Windows has quite a lot of security technology in it, but that doesn't necessarily make it a perfect fit for developing a user mode sandbox. If you had the access to kernel or administrator privileges, if you could guarantee that, then it's maybe not as much of a problem. But unfortunately, we can't always assume that you've got that access. So we have to use the facilities of the operating system to hopefully implement our sandbox for us. And this is where sometimes Windows can fail if you don't implement your sandbox correctly. So what do we want in a sandbox? Well, we can kind of quickly think of what we would actually have to write. We want something which is easy in terms of like complexity to get into. We don't want to have to write too much code. Complexity breeds insecurity. But of course, we want it to be as hard as possible to get back out again. So when that RCE pops into the browser, pops into the document reader, you want that attacker's shellcode to make it very difficult for it to get back out. We'd also like, if we can, to protect the user's data. It's not actually very good sandbox if someone can break into your application and still egress all your financial information, your passwords back out again. If you could do that, then okay, you can't get persistence, but actually your data is probably the most important thing on your computer. We have to work within the limits of the OS. The OS is only going to provide us so much we can do. And finally, we want it to be usable. If it substantially detriments performance on your application, no one is going to use it, no matter how secure it is. So in the wild, in the sort of actual application space out there, this is the sort of typical approach you'll find to a user mode sandbox on Windows. What you'll have is you have some sort of privilege boundary. You have your normal privilege, your standard user privilege, which contains a broker which is going to be used to sort of run the bits of code which actually require those privileges. You then sandbox your actual dangerous processes, the thing which is actually rendering content from untrusted sources, and you put this in this lower privileged area and provide some mechanism to talk between the two processes. And finally, everything needs resources of some kind, so you also need the resources and some way of accessing them. Now, the main way Windows actually can implement its security is through the security descriptor model. So every resource in Windows can potentially have a security descriptor associated with it, and this allows you to specify both mandatory integrity control and discretionary integrity control, and that is then used to determine how much access you can give to a particular resource. So take, for example, a file. You can say this person, this particular user, can only access this for read access or for write access. And so in order to do that, there's three main parts of the security descriptor. You have the owner of the resource, which is usually the person who created the file or the registry key or the process in the first place. You have the mandatory integrity label. This is for mandatory access control, which we'll go into a bit in a second. And we finally have the discretionary access control list, which is used for discretionary control, determining whether you've got write access, for example. Now, the counterpart to that, it's all very well having this security descriptor, but how do you actually sort of identify what permissions that person can get? And in Windows, this is done using the access token. And every process running on the system has its own access token associated with it. And this has things like the current user identifier, which is some sort of unique, in this case, a security identifier, which is this long sort of string of numbers. It's kind of like equivalent to the user ID on Unix, but it's a lot more complicated. Secondly, there's groups. So this again works like a Unix system. You have a list of group IDs, which again use security identifiers, and that can then feed into your access checks. You've got a mandatory label, and so this is the sort of counterpart to the label which is in the security descriptor. And finally, privileges. And I'm not going to talk much about privileges because they're usually not that important for normal users. So when we actually go to check for a resource access, the kernel is the ultimate sort of guardian of security access to a resource. So it has to go through a specific access check process. And this is sort of a very simple diagram. I don't know how well you can see it. Sorry. Is there a hum on the on the audio? I think I'm humming somehow. Hello? I'll just try and talk over the hum for now. Hello? Hello? Yeah, can you hear me? Cool. Sorry, I couldn't really hear that. Okay, so you've got your process. So you go through 3 different processes in this resource check. Obviously got some metal in my head or something is causing it to resonate. Yeah, so you've got the first, the integrity check. This is the mandatory control check. Then it goes through an owner check, and finally the access control check. So it splits up like this. The mandatory access control check is really simple. It takes the integrity level of your token, compares it to the resource's integrity level, and then restricts access based on that, and based on that policy. And all this does is it limits the maximum number of rights you can have. The owner check is an interesting sort of side check, which is just there to give a owner of a resource the ability to stop themselves locking themselves out of their own files. If I modified a file's access control list to block my own access, how do I ever get back control of that file? And it turns out that there's certain rights you can access, such as I want to rewrite the access control list, which as the owner you can always get. And finally, the access control list check. This is a bit more complicated. It has to go through your access control list and work out what's your actual rights you can access. So, for example, if we actually want read-write access, we'd go through the list and say, well, everyone is only granted read-only, so currently we can get read access. But we also have an access entry for read-write, and we've got write access. Right. So that's the sort of very basics of Windows access control, which is kind of necessary to understand the rest of this talk. Now, you may actually think like a really quick and dirty way of sandboxing something was just use this mandatory integrity check. Because what we can do with this is we can limit the maximum rights someone can have. So for example, you can say you can't have write access to this resource if you're below a certain level. And this was actually used by Internet Explorer's protected mode. So in IE7, which came with Vista, this is actually one of the first sort of actual application sandboxes which you could use in the real world. But it has a lot of problems, none the least that doesn't block you reading files or reading registry keys. All it does is it blocks the writing to resources. So you can't persist, but you can still steal their information, their banking details, all that sort of stuff. So it's not really a very good thing. And the trouble is, Microsoft also do not consider it a security boundary. And that's a problem, because if you're trying to write the best sandbox you can, if someone finds a bug in this process, you want sort of the operating system vendor to fix it. But unfortunately, in the general case, Microsoft will not fix bugs in this sort of integrity level model, which is a bit of a shame. So we can add some extra features. For example, if we want to block sort of access to the windowing system, one of the things we can do is we can apply these object restrictions, job object restrictions. But this also isn't a security boundary. So again, if bugs are found, there's no guarantee Microsoft will actually fix it in the operating system. But there is one supported function in Windows which allows you to make a reasonable stab at sandboxing an application. And what it allows you to do is make a new access token with more restrictive rights associated with it. Of course, the operating system doesn't give a normal user the ability to craft arbitrary access tokens, otherwise that's a massive security risk. So instead, the OS provides this create restricted token function, and this allows you to limit the access token to a certain subset. Most importantly, it allows you to add a set of security identifiers which add into the access control check and allow you to do some special stuff. So when you actually use a restricted token, the access check changes. It changes in such a way that it adds additional checks on top. So when you do the initial check, say for the access control list, you've not only got to meet the access control list check, but also these list of restricted security identifiers. And this two-pass operation makes it actually quite restrictive, and it reduces the amount of actual access you need. But we can't do everything, unfortunately. We can only sort of disable groups, we can remove privileges, but we can't change the user's identity. So it can still cause problems because you're still the same user, just now you are sort of a more restricted version of that user. Okay, so we can use this API to develop the most restrictive token you can get, something which will basically stop all resource access. No files, no registry keys, no processes, nothing. And that's great. So we now need to actually use this token. The only secure way to do it is to assign it to a new process, because there are ways of using it where you can just sort of impersonate it on a thread, but a piece of malicious code could just turn that back off again, and that's not very useful. So you need to create a new process, and there's a function to do this called create process as user. But if you do that, the first thing you'll see is the process will crash immediately, and that's not particularly very helpful. And this is because the process initialization is a bit peculiar. When a new process is created, it starts off uninitialized and it's just sort of a object in the kernel. A thread is then created, and this is the first thread to run. Now normally this would be pointing at your entry point, say your start function, your main function. But just before the process starts, the kernel does a sort of like a bait and switch. It says, yes, you're going over here, but before you do that, can you run me a function? And it runs some internal function to initialize things like the DLL loaded list. And it turns out this function doesn't really like not being able to access the resources it's expecting. And so it has a habit of just blowing up. And unfortunately, this is all sort of internal implementation details. So if it doesn't work, it crashes, it's actually quite a difficult thing to debug. It is possible, but it's very, very tricky. And so you end up spending all this time fighting against the operating system because you can't sort of see into it and fully understand how it's working under the hood. Fortunately, there is sort of ways around this, and things like Chrome use this to bootstrap this really restrictive process, but it's still a bit of a pain in the backside. So now let's think about sort of how you would attack a sandbox. So thinking about the sort of places you can attack, the areas of the system that could interact with a sandbox which may cause security issues and allow you to break out of that sandbox. And Windows is a fairly complicated operating system. There's loads of system services, there's loads of sort of areas where everyone can access resources and registry keys and all that sort of stuff. And that breeds an awful lot of attack surface. Now the classic one is system calls. So a system call is where a user mode application wants to access some resource in the kernel, such as opening a file. It'll call a special function which hops into the kernel and does that actual operation. Now if you look at, say, a modern version of Linux, say 3.6 or so, it has around 300 system calls. And that seems actually quite a lot of attack surface on its own. So we look at Windows, and 8.1 has maybe 400 or so. So it's within a degree of the same sort of size. That doesn't seem that bad. Of course, on Windows, some of these functions are completely undocumented, which is makes it harder to sort of reason about whether these functions are actually dangerous or not. But of course, Windows doesn't stop there. It's not just 400 system calls. It also includes the APIs for handling the windowing system. And that adds another 1,000 on top. And 1,400 system calls is pretty high number. And Win32k, the windowing system, has been quite a big pain point for Microsoft because it's a lot of complicated code and it just bugs keep falling out of it. And it's really, really dangerous thing to have lying around. But the trouble is, there's actually nothing you can strictly do, at least prior to Windows 8. Now, Linux and OS X have APIs to restrict what system calls can be made. So, for example, you can say, you can call open, but you can only open with this specific path matched against this particular rule. But Windows, at least up to Windows 7, did not have any equivalent feature. And the other side of attack surface for Windows, the Windows kernel, is the device drivers. So again, if you think of a sort of Unix-like system, you have /dev, and that contains all your device drivers. And it actually turns out Windows has the same thing. You just can't see it. It's not in the normal filing system. Instead, it's sort of sitting under the hood. It sits at the native object namespace, the object file system. And everything's referred to as a path. So /device/some path accesses a particular device driver. So when you go to open it, you just use the file APIs. You just say, open this file for me, and I will open this device driver. But Windows device drivers were actually implemented primarily to support things like file systems. So it has a particularly unusual behavior. When you pass this path to the I/O subsystem of Windows, when you do a create file, it first splits it into two parts. It takes the first part, which is the actual name of the device driver, so /device, say /harddisk1, and then anything after that path is considered to be what is called the device namespace. And this is just additional information. And so, for example, this is how file systems are implemented. You have an NTFS driver which exports a device node, and you can use that to access a file. When the kernel then looks up the original driver and then passes this name to the create file call, and we can actually get access to that resource. But there's a problem with this. The kernel makes the assumption that in a file system scenario, say NTFS, the file system driver is the one responsible for doing the access check against that file name. So by default, device drivers in its namespace path have no security at all. And unfortunately, there's a number of drivers which either by design or accident forget to do any access check in this scenario. And so you can gain access to device drivers even from the most restrictive sandbox you can find. Now, a good example in default Windows, excluding all the third-party drivers which may be vulnerable to this, is Windows sockets. And one of the things you would really like to restrict in a sandbox, especially one which is sort of maybe facing the internet, an attacker coming from a remote location, is you probably don't want people being able to access TCP sockets. Because A, you could talk to local host services, which might be bad, or you could talk to arbitrary resources on their local network, or egress data back out. So you think, okay, I'll write a quick test. I'll just take some code from MSDN for Windows sockets and just try and initialize the socket APIs. And so you think, okay, that should work. So you try it, and it fails. And you go, awesome. It's not going to be a problem. We can't get socket APIs to work. Therefore, there is no network connectivity in the sandbox. But of course, it doesn't work like that, unfortunately. On Linux or OS X, sockets are actually implemented using system calls. But in Windows, it's actually implemented by a device driver. It's called the ancillary function driver, which is one of the most nonsensical names for its actual function. It's the socket implementation, but it's called something completely random. And you interact with it using the device path, so device/AFD. Specifically, you're supposed to pass /endpoint. In fact, it doesn't actually check, but /endpoint, which is a namespace resource, and there's no security on this namespace. So even though you thought you were safe and there was no socket APIs, it turns out, as long as you actually know how to talk to this driver, it's actually pretty simple. And you can still get your native sockets, you can do nasty things if you've got this access. And that's bad, and there's nothing actually you can kind of do against this. There's very little you can do to protect yourself, other than, for example, firewalling rules, or there is a way in Windows 8, which I'll go into again, but it's not something you can just do by default. Right, this is my only demo I've got, but we can have a look at basically what you can actually see from, say, a Chrome sandbox, which is like about as heavily restricted as you can get. So I've written some tools to do sandbox sort of attack surface enumeration, which I hope to release after the conference, so that people can actually use them and test their own sandboxes or test third-party sandboxes and see how sort of what the attack surface may be. So we can see Chrome here has virtually no rights, everything's denied. We've got like a special restricted SID which says basically you're not going to get access to any resource, and it is pretty good at enforcing that. So I can run my tool. So this basically takes the process token and then tries to do the open requests on these device drivers to see who I can see. So I'll just run that. And that's quite a few. That's sort of 12 or 13 default device drivers, although VBox guest is obviously VirtualBox, so potentially that has issues. That's not to say that there is any security issue with any of these drivers, but it's certainly something you may then want to look at. We can actually look a bit at, we've got some of these which have like automatic names, so this 000A. We can actually sort of have a look at, see if we can work out what these are. So, for example, we can access the ACPI root object. And ACPI is the power infrastructure and that sort of stuff on a PC. That doesn't sound like something you'd want to expose to a sandbox application. Apparently there's also a fixed button hanging off that. I guess that's the power button or something. So maybe you can do some fun with that. Parallel ports. And the USB root hub you can also access. Why? Who knows? But that's the security model you have to live with, and unfortunately there's not a lot you can do about it. So there's a few other tools in that list. So for example, there's access to other objects in the object manager and sections and all that sort of stuff. So hopefully, as I say, I'll get it out as soon as possible after the conference, and people can have a play. And they'll be open source, so it'll be you can modify it as you like. Oops. Hope I went to the right Chrome. Right. Right. So a sandboxed application which can't access any resources at all is a fairly useless sandboxed application. If, for example, think about it in the browser sense, if I could not access that remote HTML page, well, I've obviously shown you can access sockets anyway, it would be pretty useless. You couldn't do anything of any function. So you need to provide resource access somehow in your sandboxing mechanism. And there's sort of two schools of thought to this. The first school of thought is you can modify the security descriptors of the resources so that the sandboxed application can access them. The other side is you heavily restrict access and then funnel all access requests through the broker. So if you want to open a file, you have to talk to some broker process over sort of a local procedure call and say, hey, can you open this file for me? And then you can do some sort of access checks against it at that point. And each has their own benefits. Direct access is definitely a performance benefit, whereas broker access allows you to mediate control a bit better. So if we think about direct resource access, what problems can this come up with? Why would this be a problem? Well, one of the big problems is giving someone direct access to a Windows resource means that they can theoretically do any supported operation on that resource. And by supported operation, basically anything the OS will allow you to do. And in certain circumstances, that's a problem. For example, think about the Windows registry. Now, the Windows registry is pretty fundamental to the way in which Windows NT works. Without it, a lot of things would not work very well. But one of the things which is not fully documented is the registry supports symbolic links. And if you know what symbolic links are, they're basically sort of a mechanism to sort of redirect access to one part of the registry to another part of the registry. But this is completely undocumented, or not completely undocumented, but more or less undocumented, but it requires no permission other than being able to effectively access a resource. So is this an issue? Well, it can be if someone else tries to access that resource at the same time and is running at a higher privilege. And I found a few of these in Internet Explorer. It seems to be the best one to attack. But I found a really interesting one where the sandboxed Internet Explorer process was able to access a part of the registry which was also used by a system service, specifically for interacting with the audio drivers. And it turns out you can start dropping symlinks in there, and then you wait around for the audio service to come up, and it will do your symlink attack. And this allows you to create keys in other locations other than the one you're supposed to allow access to, and from that you can get sandbox escape from it. So you'd hope that this was possible to mitigate, because obviously Microsoft fixed this audio server to block this symlink attack. And it is, but only if you're Microsoft. Because if you actually look at the documentation for the create key function, you'll see this reserved parameter, which apparently should only be 0. It can never be anything else. And it turns out that's not actually true. If you look at the fixes for any of these bugs that I've submitted to Microsoft, it turns out there is actually a special option you can specify, which instead of opening the destination of the link, will open the link itself and mitigate the attack. But it's just not documented. And why it's not documented? Well, because symlinks are undocumented. Therefore, why document something which you can't then use? It seems it's sort of a chicken and egg scenario, unfortunately. So you might think, okay, funnel everything through the broker. No problems with that. That's far easier, more secure, everything. We'll take the performance hit. It's worth it to make sure it's completely secure. So we say hook the create file call. If we say hook the Windows create file call rather than the sort of native layer one, we'll process the path and say, okay, you can only access directories under this location, and we can verify that relatively easily. Or we could, if Windows wasn't so esoteric in its path support. On a Unix system, everything's pretty regular. Other than, say, symlinks, you've got things like /something/something, and that's your path. Windows will take at least 5 different ways of specifying the same path. You can have relative support, you can have an absolute directory support. You've then got 2 special device path supports, which is when you prefix it with //dot/ or // and then there's also things like UNC shares to access remote resources. And covering all these different eventualities can be quite a tricky thing to do. Especially when you then throw in some fun sort of legacy support. MS-DOS has a lot of things to answer for in many, many respects. But one of them is this sort of legacy handling of things like COM support. So Windows specifies some default files. Things like COM1 always opens the first serial port, LPT1 opens the parallel port. So you think, okay, we'll add an absolute path, but it doesn't work. You put an absolute path in front of LPT1 and it still opens the parallel port. You cannot create a file called LPT1. Well, you can if you put this device path syntax, but now you've just created a file you can't delete. You can see it, but the user can't go to Explorer and say delete. It just won't work. And there's also crazy edge cases like trailing spaces. For consistency, most of the time it strips off these trailing spaces. But again, the underlying operating system still supports it. So you can still create files you can't delete, or files which match a certain pattern, but actually when they get passed to the APIs, they disappear the spaces. And then you've got canonicalization issues. You should always try and canonicalize these paths before processing them, but you have to be very careful about which syntaxes you accept, because the canonicalization works in different ways to what you would expect. So you've got things like your normal canonicalization, it removes directories, but if you have, say, //dot/, you can actually escape, you can use double 2 dots to escape out the drive letter. That seems a bit nonsensical. If you do the question mark syntax, everything is verbatim, so you can create a file called .dot, and it doesn't do any canonicalization at all. And I found a bug in the Flash broker, which is the broker for Flash in IE 11, which basically exploited this fact that there was a difference in canonicalization between one and the other, and you could do some fun tricks with that. And you can also do other crazy stuff like accessing the object namespace, access device drivers, even though you're not supposed to. It's a bit of a mess. And so actually handling Windows level file paths is actually quite a tricky prospect. And just to add insult to injury, there's things like invalid character checks. You think, okay, I'm safe from command injection because they can't put a double quote into a valid path. Well, of course, that's never the case. There's things like canonicalization, you can just get rid of it. But also crazy stuff like alternate data streams. NTFS supports a special syntax to create streams off existing files, and it doesn't honor the same NTFS file system file character checks. So you can put double quotes into an alternate data stream, and it's all perfectly fine. So, for performance reasons, going through the broker is a bit of a nightmare. So you might can come up with a hybrid approach where you create the resource in the broker, but then you pass back a reference to that resource back to the original Sandbox process, and it can do some fun stuff there. But there's, of course, risks of doing this, again, because you've now just given people access to ways of manipulating the system which they're allowed to do. Things like reparse points. So reparse points are directory symlinks on the file system. And just like registry symlinks, that can cause you all manner of pain. But all you need is a writable handle to a directory. And there's numerous attacks which have taken this and used it to break out sandboxes. Now, you're supposed to pass a special flag which says only open directories, and that should be honored, you'd hope. But it turns out Windows provides a special syntax to gain access to a handle to a directory without even specifying the right flag. So you can't even just say only allow calls to this function with this without this flag set, because it won't necessarily save you. You have to do further checks, invalid character checks, make sure you've got no alternate data streams at the end. It's all a mess. Now, when you're dealing with some sort of file, you also have to deal with the fact that just because one function takes a file path and another function takes a file path, that they actually use the same file path under the hood. And again, for legacy reasons, that's not something Windows is always consistent about. One of the bugs I found in IE was there was a ability to run a DLL, so load a dynamic library into a higher privileged process, but it made sure it was signed first. Now, ignore the obvious race condition in this. There was more to the code. This is a very simplified piece of code. But the isSigned file passes it to create file, it verifies the signature, and it then passes it to load library, which is the function to load a library into a Windows process. So you go and look at the API documentation, and you'll see at the bottom, I don't know how well you can read it, it says if the file name is omitted, then we'll add .dll to it. But if we put just a dot at the end of the file name, we'll remove the dot and do it undecorated. Okay? But it's only for module names without a path. Therefore, you're assuming only if you specify just a single name, not a full path. So you test this out. You pass that in with a .dll extension, works as expected. You pass one in without a .dll extension, and it sticks DLL on, even though the documentation said it shouldn't do. And obviously, just to prove, put dot, gets rid of a dot. So you can get something which opens in create file and is signed, and then it opens a completely different file when it goes to actually do the DLL loading. So one of the final things I'm going to talk about is a very quick sort of run through of one of the weirdest bugs I found in Windows. It's not a bug in the sense of it's by design, but it's completely unexpected functionality. Now, the kernel supports many different resource types. So you've got the standard files and registry keys, but you've also got things like sections, and sections are like shared memory objects. And you can use these shared memory objects to pass around, say, larger bits of data between your normal process and your Sandbox process. So in the Chrome case, I found that it was sharing a script between the broker process and the Sandbox process for the purposes of, it was like a grease monkey script if you've seen those. It was allowing you to interact with the rendered page. And it did this, and the idea was you couldn't write to this section. So it created it writable in the broker and then shared it read-only to the Sandbox process and relied on the operating system to stop the Sandbox process elevating its privileges and gaining write access to that section. But this was done without naming the section. You can add like a special name which allows a other process to access it. And it turns out certain classes of Windows resources opt out of security when they have no names. As in, it's not, well, not even just opt out. Literally, it will not do any checks whatsoever if there is no name associated with that file, with that resource. And it turned out section objects was just one of those resources. So you could, in your Sandbox, take this read-only section, convert it into a writable section, and then do a sort of a universal cross-site script against every page which got rendered. And in Chrome, there's certain rendered pages which have higher privileges than others. And so you can use this to break out the Sandbox. So one of the final things is talking to the broker. So the broker obviously needs to be able to communicate with the Sandbox process in some way. And Windows provides numerous ways of doing this, and there's a lot of sort of risks associated with this. One of the ones which are sort of, again, it's used by the Chrome Sandbox and others, is named pipes. And you can create a named pipe and then reopen it, and you can just use this as a binary channel between the two. But of course, if you've got a super secure Sandbox, you know you can't create these named pipes directly. So you need to pass it to the broker and get it to do it for you. And there's a special function, create named pipes, which it does what it says on the tin. But interestingly, when you specify the name for the pipe, it specifies like a full path, a device path. So, for example, the Chrome API was doing this. It was checking that it began with a certain prefix, //dot/pipe/Chrome, and would only allow you to create those pipes. But I've already shown previously, when I was talking about the file APIs and the support for paths, that this is a canonicalizable path. Even though it's completely useless in this scenario, this actually can be canonicalized. So you can add a // in there, bypass the check, but still open a completely arbitrary named pipe. And that's completely unexpected. So those are some of the problems with Windows. Now, is it actually getting better? I've alluded quite a few times to Windows 8 and Windows 8 having extra features in there which may actually make things better. One of the things is an API called Set Process Mitigation Policy, and there's a function to effectively remove access to Win32k. And that just strips out over 1,000 system calls automatically. Of course, there's still potential problems in there, and sometimes if you're actually relying on Windows 32k support, you're not going to get very far if you just completely disable it. But it's definitely an option which can be used. And there's also something called the low-box token. So you've got normal access tokens, you have restricted access tokens, which were introduced in Windows 2000. And finally, Windows 8 has now a new low-box token, and this was designed for supporting Metro applications, the sort of full-screen applications. And you can do some fun stuff with this. One of the things is you can add capability identifiers. And it kind of works like the restricted SIDs, but you can do things like you have the capability to talk to the internet. So if you don't have that capability, socket access is blocked. Even though you can access the device, it's actually now blocked, which is actually quite a cool feature. And it modifies the access check basically like it does for restricted SIDs, other than now it's the capability SIDs. But there's actually an interesting bug in this support, or a feature. I'm not quite worked this one out yet, in that they've actually broken the integrity check. The integrity level check, even though it wasn't a security boundary, was still actually quite a valuable feature to have in the access check. And they've broken it. So all tokens for low box tokens have this low integrity label. But for some reason, the level check hard codes all token resource integrity level checks to medium. So you can access any resource at medium and bypass this check. And actually, this was actually one of the main reasons for a few bugs I reported in the IE Sandbox, where you could access resources with write privileges when you shouldn't be able to. Because if the integrity check was there, it would have actually failed. And so they've gone so far and done some cool stuff, and then, in my opinion, broken some of the actual useful functionality along the way. And I don't know why they did this, but there we go. Now, in Windows 10, there sounds to be some cool stuff coming along for process isolation. One of the things which has not really been talked about much is pico processes, or sometimes called drawbridge when it was originally in research. And this is actually sort of a per process isolation technology. So it might be really cool. Windows 10 may actually bring some really big gains for a sandboxing application. Unfortunately, it's not currently available or documented, so we'll have to wait, I think, on that one. But hopefully, I'm hopeful for the future where Windows 10 may actually be the best operating system for sandboxing, possibly on pretty much any other platform. So that's the end of my talk. Sorry about the buzzing at various points. If anyone's got any questions, I think there's not much time left, but I'll be around for the next few days, so you can always catch me and accost me with questions at that point. So thank you very much.